Tony Paul here. Today I'm going to show you how to make one of these. What is it? Well, they're known as LVT, Linear Velocity Transducer. That is, it measures the relative velocity between this moving part and this fixed part. So what would you use one of those for? I've built what's known as a shock dynamometer, which is a machine for measuring the characteristics of vehicle shock absorbers, in my case motorcycles, in which the shock absorber is cycled over a range and measurements taken of the force, displacement and velocity. This will cycle with the shock absorber and give me a voltage proportional to the instantaneous velocity at any particular point. Other uses for LVTs include fitting on some types of CNC machine to measure drilling in feeds and similar things to that. They're widely used in industry for a variety of purposes. It's a very simple device to make and to use. It mainly consists of two coils, like this first test one that I did. You can see we've got one coil here and one coil there. Now, if the coils are wound in the same direction, the two coils will be connected as I've shown here. The bottom of this, the top one will be connected to the bottom of the lower one, and the output will be between the wires at the top of each. An alternative way of making it and connecting it is if this one, for instance, is wound clockwise and this one is wound anti-clockwise, then they'll be connected as shown here. The centres will be connected together and the output will come from the two ends. Inside these coils we have a longish magnet that will fit up inside. This contains the coils, this contains the magnet. Looking at this in more detail, this is just a test coil I made with some copper wire that I had here. The magnets, these little rare earth magnets, are 8mm diameter, 25mm long. Now I needed longer ones, but you can easily just join them end to end. There's three here which I used with this test one. As you can see, the length of the magnets is shorter than the total length of the coil. In the real one, the length of the magnets needed to be longer because I wanted 100mm of movement, which meant I needed 125mm at least of magnet, so I've actually got 5 of those magnets inside here. Although I made my working magnet out of multiple magnets to get the length I needed, 3 in this case and 5 in the case of the finished LVT, they just act as if they're one magnet of this length. We can easily see that with this screwdriver test. If I bring it near the end, it's strongly attracted. I come to the other end, much the same, and it'll easily hold the magnets up. If I come to the middle, there's nothing, no force trying to hold the magnets up. If I move along, you can see when I get close to the end, that's where the attraction is. So it just acts like one magnet of the full length. The ingredients to make this are very, very simple, very cheap. Firstly, I've got a little bit of plastic irrigation hose which I used as a former and support for winding the coils. I needed something to hold the magnets, so I've got this piece of aluminium tube which is just a millimetre or two larger than the diameter of the magnets. I drilled that down just a couple millimeters deeper than the length of the magnets. I think you can see that there. I put some epoxy glue on them when it was pushed in, and then in the lathe, as we'll see, I just rolled the edge over to provide a mechanical stop, so the magnets were held in positively. As you can see on this one, the coil's hidden inside this other plastic tube for protection. That was just some normal plumbing water tube, which is easily available at any hardware stores. Then the final piece was just some copper coil winding wire. So very few ingredients, very cheap. To finish this part off and to enhance the protection of this outer tube, I filled the gap between the inner tube with the coils and the outer protective tubing with some epoxy resin. Actually, it was this West Systems epoxy resin. Actually, I got into a heck of a mess doing that, because the method that I had to stop the resin coming out of the bottom when I was pouring in at the top failed, and as I was pouring it in, it was coming out the bottom just as fast, which took me a little while before I realised what was happening. It was a mess, not pleasant. I'll just give a quick idea of how this is connected up to get some useful readings from it. If this is our LVT here, then the output of that is of the order of a few millivolts. So I pass that through an instrument amplifier chip. They're only 50 cents or something like that, very, very cheap. Then that goes into a lab jack, which is a data acquisition system, or DAQ, and then I pass the output of that into a PC to be interpreted by the software that I've written, which does all the analysis for the shock dynamometer. The rest of this video will be dedicated to showing how I made the LVT, and at the end the results that it produced. This is the coil winding setup. I've already done approximately half of one half of the LVT. There will be one coil here, it starts here, will end up here, and then the other half will start here and finish back here. The coil of wire is just simply on this rod here, which I've got jammed in behind the cross slide. There's no tension on that because I'm going to provide that with my fingers. I'm just going to run it at quite a low speed. If the coils aren't coming out as nice as the first ones, then I'll stop and push them together, because it's very important that the coil is wound evenly, otherwise the voltages produced will vary. For the same speed, they will vary depending on where it is in the stroke. Now just zoomed in. There we are, you can see it's going quite nicely. I've just got to keep my nerve and keep it steady and stop. Right, well there we are. I overran at the end a little bit, but that's no big deal. I'll just take that back a couple of turns. Okay, so now I've finished both coils. I'm pretty pleased with the way in which they've turned out. It's a pretty even wind. What remains now is I'll put some transformer varnish over these before taking it out, and then laying the loose wires along here and varnishing those as well prior to putting some termination at this end. With it here we can see a little bit how it is going to function. This is the magnet that I'm going to use, which will slide up inside the tube that the coil's wound on. Each of these magnets is 25 millimeters long, so the total assembly is 125 millimeters, but I'm only aiming for this LVT to have a range of 100 millimeters. But the reason for the extra length is fairly obvious. If we say this is the center position, then if I move that 50 millimeters one way, half of the 100, which will be to here, we can see that there's some overrun with the coil on this end. This is to allow for end effects of the magnet. If we exaggerate and say that on full stroke the magnet came out here, we can see that the magnetic effect from the pole on this end will actually be outside the range of the coil, so it won't be inducing that much voltage into the coil. So as we come back from that extreme situation in, we can see here if it just came flush, we would still have some sort of end effect. So by having it so I've got quite an overrun of coil on this end, on each end rather, then the end effects are contained within that. The same thing happens in the center. I don't want to come past with this pole needs to stay within this coil without introducing any end effects. So I've got a similar margin here, and the same when we move up to the other end. We've got this margin on here, and now the end of the coil somewhere around here, where we've got an excess of coil. Now I know you've all been dying to ask why I needed to make two separate coils on here instead of one long one. If this is the magnet that's going to slide up and down inside this tube, most of the magnetic effect is concentrated at these two ends, and when you move a magnet inside a coil, you'll induce a voltage in the coils that are in the region of the magnetic field of each end. So if this was one long coil, imagine this is the north pole, and if I move it to the left like this, say for instance it would generate a positive voltage in this end. At the other end we've got the south pole, but it's moving in the same direction, so that will induce an exactly opposite voltage in the coil also. So we've got a continuous coil with a positive voltage being generated here, an equal negative voltage generated here, so they'll cancel each other out, and we'd measure no effect from this moving. There are two ways around this by separating the coil into two. One method is we can wind one of these coils in the opposite direction to the other. So let's say one is wound clockwise and the other one is wound anti-clockwise. Then if we join them together here in the middle, what will happen then is as we move the magnet, because this one is reversed, when this one generates a positive voltage, this one will also. So they'll add together and we get the result that we want. The other method, and it's a method that I've incorporated here, just simply for ease of winding on this fairly crude coil winding setup, I've wound them both in the same direction. So instead of joining the two in the center, which should just be the same as one long coil, I join this end to this end, the joints here, and I bring a wire out through a center tapped connection, which is useful in the processing electronics, and the signal comes out of the other two wires, one here which should be visible, and the other one from here which is around the back. What happens now is they're both wound in the same direction, so as this moves this way, it generates a positive voltage here. This end, being the south pole, generates a negative voltage here, just as it did before. But now they're not connected in the center, they're connected end to end. So in effect I've reversed this. So again, those two voltages add together and we get the result that we're looking for. The next stage is to make the device that will hold the magnet. The magnets will go in here with a bit of epoxy. The final thing, you can see this small gap here, and then that will be rolled over for security. Now the magnet bar is being glued up in the side it's holding tube. All that remains here now is just to roll over this edge to give an absolute positive location for the magnets. I'll be doing that with this, what I call my aligning stick, which has got a ball race on each end, which is useful for knocking things into alignment, but also for a job like this for rolling over. So let's see how that goes. That's made a nice little rolled edge there, which has reduced the escape diameter, so there's no chance the magnets can fall out. Well, having got the main parts done, I got fairly impatient to give it a quick test and just to see what its sensitivity was, what its output was per unit of velocity, or exercise the unit as a whole. This is just taped on, but as we saw before, there's virtually no force on this, and you can see it's rigid enough for present purposes. So that's basically what happens. Now we need to check the output. So I've got the signal going into an oscilloscope, got 50 millivolts peak on one side, or 100 millivolts spread between the plus and minus peaks. Now for my purposes, it's the overall spread which is important. Now that we've got the main parts finished off, we've got the coil assembly here and the magnet rod, which we've seen will work up and down inside here. Let's look how it's all going to be boxed up and finished off. We'll zoom in on the individual components to see that a little bit clearer. This whole thing is going to be potted later. I've made a change to this magnet rod that I had before. I've actually got a carbon fibre extension on it here for operating. If you remember, the original one was all aluminium, but some use extension rods directly onto the magnet, and they use extension rods that have zero or low conductivity. The reason for this is they claim that there could otherwise be a problem with eddy currents. Now eddy currents are currents that are induced into metal surrounding moving magnetic fields. Because the magnet is actually moving with this, I must say I'm not entirely convinced that eddy currents would be a problem, and in fact my testing has shown no particular problems with linearity, accuracy, or even getting sufficient voltage. But it still seemed a better idea if I could make this whole thing in plastic. Unfortunately, I didn't have any suitable plastic around here at the time, so what I did with the original one, this was like this, except the magnets occupied that much space. I cut it off here, drilled up in and glued in this carbon fibre rod. Now let's see how this is all going to go together. Oh, before I get away from that, so I've made a little end fitting here which has been drilled to go over the end of this carbon fibre rod, and the other end is tapped so I can put a bolt or some other sort of fixing there. This isn't glued on at the moment simply because this hasn't been cut to length. I'll do that when everything's finished and I can see how long I want it for mounting and what's the minimum length I can make it and still let the thing slide over its full range inside the coil. Using the coil system like this, other than in a test situation, which is all I've done so far, it'd be pretty vulnerable. So what I'm going to do is put this up inside this tube and then fill it all with epoxy to make a very solid assembly. Now on the coil, you can probably notice I've glued 3 little pieces of plastic here. What therefore is to keep that coil centralised inside this tube. At the top of this tube I needed some end fixing, and I turned up this little plug to go in the end. That's been drilled and tapped 6mm, so I can put in something like this rod end, so that when that is glued in place there, I've got a nice attachment. For remember, there's virtually no load on this at all. The magnet just slips very easily. This will fit up inside here. Before that's done, I'll slip this connecting wire down through the hole, and while it's easily accessible, I'll solder that onto the ends of the coil here, and then push the coil up and pull the wire out through this hole until it's flush at the end. And then that will seal on the O-ring, and I'll pour the epoxy in, put a little vacuum tube over here to suck the air out of the epoxy, which should give a very good support for this. But this has already had several layers of varnish on, so even if there are some air pockets in the epoxy, it won't really matter, because there's no real vibration or other mechanical loads on this, and the varnish will stop any of the coils moving. I've now threaded the wire through. Wires are soldered at the top of the coil. This is now that they're joined in this way. It's the most delicate part of the whole operation, because it would be very easy to pull the wires off, so I have to now be careful how I handle it. The next stage is to thread it through and pour the epoxy down. I'm not going to film the potting part of it, simply because it could easily turn into quite a mess, and the last thing I want to have to do is fiddle with the controls on the camera with very sticky hands. It's just as well I decided not to film the potting, because I did get into quite a mess, and the whole thing was extremely messy, and I wouldn't have wanted to have touched the camera with that going on. At the bottom I had no ring in the annulus between the two tubes. The intention of that was to seal against the resin that was being poured in at the top. Well, it didn't do that terribly well. Resin started leaking out the bottom. I'd put quite a bit of resin in before I realised this, because I thought it was just running down between the two tubes in here. The thing was, I was able to fill it. I then put the plug in, the excess squirted out through the threaded hole, and I left it to set. Came back in this morning and cleaned it up, acetone, sorted that out. Then I had to re-tap the hole, because that was full of epoxy. That's part now is finished. It turned out pretty well. We've got a good tie for the cable. I checked for continuity with the wires on the other end, and everything seemed okay. So I finished off the magnet rod. I glued on another adapter on here, which was threaded to take the rod end. So now that goes up in there. It hits on the rubber stop up inside before it hits here. I can put a rod end in up here. Well, actually, there are different ways that I can mount this. I could put a clamp around the body, but so I've got all those options open to me. So if I put that in there, then I have a rod end at each end, and here's the finished item. All that remains is to connect up to an instrument amplifier and measure the data. On the shock dyno, I originally used what's known as a string pot, which is just a multi-turn potentiometer, for measuring the displacement. But you could just as easily use a linear potentiometer. Both of them are shown here. Now, from the displacement information, it's possible to put that through a process known as numerical differentiation, which will produce velocity information. Problem is that differentiating the displacement to get the velocity will enhance any noise which is in the original displacement signal. This is the reason that I built the LVT, so that I could measure the velocity directly. Now, these graphs show the as measured data on the left from the string pot to get the displacement information. On the right hand side is the velocity signal as derived from the LVT described in this video without any filtering whatsoever. These next two graphs show the velocity as calculated by differentiating the previous displacement information, and you can see the signal is quite noisy and will require quite a bit of filtering to make it usable, but the filtering will also filter out useful information. On the other hand, on the right hand side is the displacement as calculated by integrating the velocity signal, and we can see that that is even smoother than the directly measured displacement data with the string pot. So I now use the LVT exclusively on the shock dynamometer. This gives me the velocity signal direct and a very clean signal when it's been integrated to produce the displacement information. If you like this video or any of the others, please share, subscribe to my channel, and don't forget to click the button to receive updates of any other videos. Thanks for watching.